You're now about to learn about a new type of number called complex numbers. And part of a complex number is a number with, I think, the rather unfortunate name of imaginary number. An imaginary number sounds like it's almost silly to work with, but these are a lot more important than they appear. Anyway, what in the world am I talking about? We countered earlier the idea that there is no real number that handles something like the square root of -49. But it turns out we have need for numbers like this. We have a reason to calculate and work with these kinds of numbers. And it's because they show up in real computations. Specifically off the top of my head, anytime you model something that vibrates or oscillates, like a spring bouncing up and down, or a string vibrating, or possibly AC, DC, alternating current, electrical current, alternating current, oscillates between positive and negative. Oscillations, the mathematics of that, it turns out in calculating with that stuff, you end up with these kinds of numbers. And so there's at least one area where these find real-life application. People need to be able to work with these in order to solve real problems. All right, so the reason they come up in this algebra course is because in the next chapter you learn how to solve quadratic equations, which are second-degree polynomial equations. And some of these equations, their answers involve numbers of this nature. And so I can give you a quick example of that. The equation x squared plus 49 equals to 0. This number is, turns out it's a solution to that equation. So there's an equation with an imaginary number for an answer. Well, it turned out in the somewhat farther past, deep past, hundreds and hundreds of years ago, when mathematicians encountered problems like this, they just ignored them because they said, well, that answer doesn't exist in our real world, so it can't possibly have an application. And it wasn't really until the 1500s when people tried to found that they could solve third-degree polynomials. For example, x to the third power plus 6x plus 9 equals to 0. I don't know what the answer is to that. It's very complicated to solve those. But it turns out that some of these problems, we know they have real numbered answers that could be expressed in terms of decimals. But they found out in the 1500s that when they solve these problems in symbolic form, and they're very complicated to solve, but they can be solved, that some of the answers they were getting involved square roots and negatives, even though that this long number they got, this long complicated looking expression, was actually a single decimal real number. It involved, as part of this expression, square roots of negatives. Must have been very puzzling because up to that point they thought those numbers were just fanciful. They were imaginary and useless. So it created quite a puzzle back in the around the 1530s, 1540s when they first encountered that. All right. Well, the traditional way to start this is to introduce you to the imaginary unit. The imaginary unit is I, letter I. So I is by definition. So when you see a triple equal sign in math, that means by definition is equal to the square root of -1. And I have to define one other number here in order to work with this. I squared, by definition, is going to be -1. Now, actually a former intermediate algebra student of mine called me on this one day in class because I made the observation, well, if you square a square root, you get the number inside, right? So if I took I and said, well, that's the square root of negative 1. If I square both sides, then what happens when you square a square root? Doesn't that cancel the square root? Well, she immediately saw that there was a problem with this. She said, well, wait a minute. When you square this, don't you have the square root of negative 1 times the square root of negative 1? Says, yes. And by the rules we were looking at in a previous section, we're able to multiply these together. Yes. And when you multiply negative 1 times negative 1, you get positive 1. Uh-oh, because the square root of 1 is positive 1. So we run into a real interesting problem here. The rules of arithmetic, as we know them with real numbers involving square roots, begin to break down when we go to these complex numbers or these imaginary numbers. And in fact, the problem is that this step doesn't work from here to here. We can't jump over to there, because otherwise we have a real problem. Is I squared equal to negative 1, or does it equal to positive 1? It can't equal both numbers at the same time. So it turns out life works out a lot better if we just, by definition, declare that I squared is equal to negative 1. And in so doing, then we have to declare that the rule that says we can combine numbers together when you're multiplying square roots is no longer works if both numbers are negative. So, to give you an example of that, if you had the square root of, let's see, let's make it negative 9 times the square root of negative 16. What should it be? Well, okay, it would be wrong to assume that this is the square root of negative 9 times negative 16. Negative 9 times negative 16 is positive 144, which is equal to 12. What has to happen is this. We think of the square root of 9 as the square root of 9 times the square root of negative 1. And we think of the square root of negative 16 as the square root of 16 times the square root of negative 1. In other words, this becomes the square root of 9 times letter I. And square root of negative 16 becomes the square root of 16 times letter I. And so what do we have? We have 3i times 4i, which is 12i squared. And there we go. We've defined I squared to be negative 1. So this is really 12 times negative 1, which is negative 12. So I don't like to introduce real complicated, confusing stuff like this, but it's something we have to live with, the complex numbers. It turns out they're incredibly useful. As I mentioned, they have applications in the real world. In mathematics, complex numbers explain an awful lot. It's a very robust area of research currently in mathematics. There are researchers who work in the complex number area, and some of that's associated with topology, and it turns out there are applications being found for this as we speak. So it's an important area in mathematics, and I have to concede you have to go pretty high in math in order to actually bump into all that. But at least you get a little exposure here to this new set of numbers, and we'll talk more about this in the next video.